from week 9, right?
Yes, sir.
Okay. So like from which part?
Activity question.
Okay, activity question. So okay, so I'm planning to discuss few activity questions. So from 9.1 or maybe
Sir, 9.5 and practice question as well.
okay, 9.5. Okay, so yeah, so mostly like I'll discuss all these things in the end, like because yeah, I'll go one by one. Like from planning to discuss mostly today, I'll discuss this partial derivative and limit. So Tuesday probably I'll discuss this some questions from this directional derivative and gradient. But anyway, you can ask your questions from directional derivative and gradient in this session also. But yeah, so the slide that I prepared, actually I have taken question from partial derivative and limits and continuity. Okay, so we'll start now. Okay, so the first question is if so one function is given. So this is my function. A minute. So the function is given. So f of x is e power 4 times x plus 1 into sine 7x minus 4y. So it's given that if this condition holds, then what is the value of this k? Okay, so we need to find the value of this k. Okay, so just let me recall the definition of partial derivative. So how you define partial derivative? It's basically it's more or less a single variable derivative. So suppose you have some map. Let's say it's a map from R2 to R. So this is a function of two variable. So so this is a function of two variable. So the partial derivative with respect to x at the point x naught and y naught is. So we denote this partial derivative as f of x x naught y naught. So this is, so we can denote by this symbol. So this is nothing but limit h tends to 0 f of and obviously provided that this limit exists. So basically, as you can see, it's so as you can see, we are not changing this variable, the second variable, because we are actually doing the partial derivative of with respect to x. So we are not changing this second variable. So basically, it's basically the derivative of f with respect to x, and keeping the y variable as a constant. Okay, so when we're doing the partial derivative with respect to x, then basically we're treating this y variable as a constant. So this is a constant for us when we're taking the partial derivative with respect to x. And similarly, when we'll take the partial derivative with respect to y, then we have to treat this x variable as a constant, right? So for example, if I take this, maybe say this function, if I take the partial derivative with respect to x, so this is my x. So this is, so when I have some terms in x, then I will just do the single variable derivative. Whatever you have done in single variable, you have to do accordingly. Okay, so the derivative of x with respect to x is basically 1, and here we have to treat this variable y as a constant, and you know the derivative of a constant is basically g, right? And similarly, up, maybe say this function, say y square x. So if I differentiate this function with respect to x, then I have to treat this one as a constant. Okay. As a constant. This is a constant. And then if I apply this rule of this single variable differentiation, then what I will get? Y square times dx by dx, and this derivative is 1, which is x squared. So the partial derivative of this function with respect to x is y squared. Okay. So clear, like how actually we are doing this partial derivative. So when we are doing partial derivative with respect to x, then we are treating all other variables as a constant. Okay, so when we are doing partial derivative with respect to y, then we are treating all other variables as a constant. Okay. So okay, so now let's try to solve this question. So f of x comma y is e power 4x plus y. So into sine seven x minus 4y. And what we need to find? We need to find the value of k. So some equality is given, 4 times partial derivative of with respect to x plus 7 times partial derivative of f with respect to y is k times f of xy. Okay. So 4 times partial derivative of f with respect to x 7 times the partial derivative with respect to y is nothing but k times f of x. So first we'll try to compute this. Okay. So okay, so first try to compute d of a with respect to x. So again we'll apply. So yes, answer is 40 true. So again we'll apply the product rule. So we are so basically what we are doing the derivative of x by treating this y as a constant. Okay, so we'll apply this product rule because we have two functions over here. So this is f. So this is maybe say g time h. Okay, so we'll apply the product rule. So first we'll take the partial derivative of g with respect to x. So that is nothing but e time e power into if I take the derivative of this 4 times x plus y, then what I'll get? 4. Okay. So then so the derivative, so what is this, the formula? Sorry, so if I apply the product rule, then what I'll get? This time sine into d of dou of a dx into so now, so this is this time sine 7x minus 4y again e times x plus y into, so what will be the derivative of this one with respect to x?
Cos 7x minus 4. 7 sin cos 7x minus 4.
Cos
x minus 4 into 7.
7 into 7, right?
Yeah.
So this is so this one is partial derivative of f with respect to x. Okay, so next we need to compute the partial derivative of f with respect to y. So if you go if we do the same thing, like treating x variable as a constant, then we'll get this one times 4 times sine 7x minus 4y plus cos
7x minus
4y
into minus 4.
minus 4
E power.
yes, e power 4
into
x plus. Okay, so so now what we need to do, we need to add these two things. Okay, so 4 times plus 7 times df of x dy. So if we add, then what we will get? So this is what, like we have to multiply 4 over here. So we'll get 16 e power y into sine 4y plus 28 plus y into cos 7x minus 4y. Then I have to multiply 7 with df by dy. So then what I will get 7, which is 28 plus sine
E
power x into sine minus minus 28
E power 4 express cos 7x.
cos 7x minus 4, right? So this is our final thing. So this one and this one will get cancelled. Okay. So now just a minute. So now, as you can see, this is nothing but f of xy, right?
Yes.
And yeah, so this is also f of
X.
xy. So now if I'll add, then basically what I will get?
44 f of x.
44 f of x, right? So if I add these two things, I'll get 44 f of xy. So the basically the value of the k is, so here the value of k is 44. So any doubt on this calculation, like what we are doing here? So it's basically the one variable calculation. Sorry?
No, sir.
Yes.
This is clear.
To the doubts.
So any doubts?
No, not doubt. I just want to see the
Okay.
questions. Can you go to the top first page? So, how do I get hold of this PDF?
Sorry, you are not audible. Like I can.
How do I get this get this worked out? This one PDF. It's after the session.
Can you please say it loudly? Like still, I can't hear you.
So I was saying how to get this solution PDF after this. After the session, how to get this live session?
Solution of this PDF first. This
Okay, we'll upload it in the portal. Okay. Okay, so it's better if you still I was not able to understand what you are saying. Okay.
Yeah, that's what the same thing.
Yeah. So yeah, after he said only then only I realized what you are saying. Okay, so it's better if. Okay, so
cancel this one, sir.
Sorry.
Just hold on. Right. No. You're canceling the 28. Right here.
This one with this one, right?
Yeah. See, because the first one is 28 e power 4x plus y times cos 7x minus 4y.
Yes.
Okay. Oh, here also cos. Okay.
Yeah. It's basically a minus.
I was thinking this is a sign. Okay.
This is basically a minus. Yeah.
Right. Okay.
Okay. So. Okay. So.
In the same exercise, last problem also similar to this one.
Which one?
Last problem.
Mm,
Same exercise. 9.2, the last problem.
9.2 last one. Yeah, this is basically the last problem of 9 point. They're basically the same.
Same question.
Yes, yes,
Yeah, it's the same problem.
yes.
But if you're showing a different problem, how is that?
No, sorry, like they are basically the same problem. The 9 point, this is basically 9.2 question number 10. This one is basically 9.2 question number 10.
9.2, question number 1. I have a small problem. Can you just check that one? I get the answer 8, but the real answer is 10.
So, okay, so the thing is, okay, like,
Sir, can you please explain the cancellation part alone, sir? I'm not getting it.
sorry?
Can you please explain about the cancellation part? How you are cancelling it, sir?
No, like this is the negative part of this, right? This one is the, so this is basically A, this is basically minus A. So if I'll get cancelled, then I'll get 0, right?
Saying it's minus A, I'm not getting it, sir. Sorry.
No, this is
Minus 28 e power 4.
Okay. Fine, sir.
this,
Fine.
yeah. So I think this is E power actually. Okay, it's not E times.
Okay, sir. Fine.
So okay, so so let me discuss one more question related to this. YZ. So we need to find the rate of change of the function f at point 1 to minus 1 with respect to the variable z. Okay. So basically what it's basically asking, you need to find the value of the partial derivative of f with respect to z at point 1 to minus 1. Okay, so first let's try to compute this function. So this is nothing but okay, so as I have already said, when we are so when we're doing yeah, so these are basically, yeah, so you don't have to tell the answer in chat box. Okay, it's fine.
6z minus 2y.
So okay, so this is constant. Okay, so when we're doing partial derivative with respect to z, then we have to treat x and y as a constant. So then this term is basically, it's a constant. So then the derivative is basically 0, right? And again, here, as you can see, there is no term of z. So then we can think this as a constant. Then again, the derivative of this one, partial derivative of this function with respect to z is also 0. So now we have this. Now we have a term containing z square. Okay, so then again, if you compute the partial derivative, then what you will get 6z. And again, we have to think this as a constant. So this is nothing but a constant time z. Okay, this is nothing but a constant time z. Okay, so when we'll do the partial derivative, what you will get?
Minus
Minus
2y.
2y.
Minus 2y. Okay, so then this is my function 6z minus 2y, right? So then what we need to do, we need to just evaluate this function.
Yeah, okay.
So 6z, so z, the value of z is basically minus 1 here. So this is minus 6 and minus 2y, and the value of y coordinate over here is 2. So then it's minus 4. So then the answer is -10. Okay.
Sir, computationally you got it, sir.
Sorry.
Computationally you got this actually. You understand how we are getting this. Now, conceptually, this would be the same. This just you wanted to know conceptually. This result will be the same. Let's say for let's say someone learning for the first time, so it goes there and puts only the z coordinate as -1 plus h, and then takes E3. That is the third.
Okay. So okay.
0, 0,
So
1.
again.
F of a plus h minus f of. If you do roundabout and somebody arrives at this will be the same as that, right?
Yeah. If you go if you follow the definition, like the definition, then obviously you will get this result.
Those who will match, right?
Yeah. Certainly they will match. Yeah.
Thank you.
But okay, so the thing is, if you do in that way, then it will be lengthy. Like you have to do.
Yeah, it will be lengthy.
Yeah.
No, I just want to.
No. Certainly they will match. Okay, that is how we define. Yeah. So. Okay, so okay, like I guess now you can solve like the questions related to this partial derivatives.
Sir, I joined little late. Hello.
Yes.
Can you just show the first part of this so that I'll just take the screenshot?
Okay. Anyway, we are going to upload it, and yeah. So the thing is, even you can go back and take the picture. Like it's.
So I have a doubt in activity question 1.
Yes.
Sixth question.
Is it related to partial derivative?
It is related to one second.
No, if it is not partial derivative, then I am not going to solve it now. Like I can solve it in the end. Okay. So because he asked something related to partial derivative, that's why actually I have explained it now. Okay, so
it's basically multi-valued vector. We have this, right?
No. My question is whether it is related to partial derivative or not. Like.
1 second. This question is actually we have to find out from the set of equations how many are vector valued multivariable.
Okay, so that I'll discuss in the end. Okay.
Sure.
Yeah. So
later that was.
Yeah. So okay. So the next thing is now it's okay. So now we have this function. So this is more or less a piecewise function, because it's we have defined it that if x and y is not equal to 0, 0, then the value of the function is x times y by x square plus y square. And if x and y are 0, then this value of the function is 0, 0. Okay. So now the thing is, it's asking you to find the partial derivative of this function at point 0, 0. Okay. So now actually you cannot use this trick. Like you cannot simply differentiate this function and you cannot compute the partial derivative. Okay. So now you have to go by definition. Okay. So Krishna Mohan is saying like this was solved by Sir in video.
Sir,
Yes,
I would
sir,
like
please.
to know, sir, one thing. Why you are saying that we cannot derivative it directly at x equal to y equal to 0? So why we can't say that rate of change will be 0 directly if that fxy equal to 0?
No. So the thing is, okay. So the thing is, what is the problem? Okay. So we just know the value of the function. Okay. So my question is how you will do it.
that I got it. So we need to first make a derivative of this function f dash xy, then put the value 0, 0. Maybe that is the correct answer.
No, but the problem is when you will differentiate this one. So you are saying you will differentiate this one.
Yes.
No, but the problem is this is not the value of the function at 0, 0. So you are differentiating something else. Then you are putting if
Okay.
so,
Okay. Got it, sir. Got it.
Yeah.
Sir.
So
I am wrong.
So the thing is, if you know the value of the function in an open ball, okay. So in an open ball containing 0, 0, okay. Then only you can apply that trick. Okay, but you certainly you don't know the value of the function. So whenever you are taking this one, then certainly this value of the function matches with this over here, but certainly it doesn't matches with this at this point. Okay, at origin this is not defined
because it is 0 to 0 by 0.
Yes. Okay, so if you can, like, if this function matches with the value over all the okay, if the function matches with the value in this region, complete region, then actually you can apply that trick. Okay, otherwise you can't.
So sorry sir for disturb you, but what is open ball? Actually, I don't get it. Actually.
It's basically a circle. You can think of as a circle, okay, containing that point. Okay. It's a small, like you can take a circle, like this is a open ball. This is a open ball containing 0, 0. This is also a open ball containing 0, 0. This should this should hold for at least one open ball. Okay, it doesn't matter whether that ball is big or it's a small ball, but it should hold for at least one open ball. Okay.
So it should hold by at least for one open ball means what it means?
At least you can get a circle, okay, such that the value of this function, let's
Must
say
be valid for every point inside the circle.
value of this function is same as the value of this function for all x comma y in this ball. But
okay.
This is not true, right?
So why it is not true, sir?
Because
how you...
if I take 0, 0,
okay, so then undefined is coming.
Yeah, so here I'm getting 0, but this one is undefined.
So you would say this is not continuous. This is why you use the word continuous, not continuous in the...
Sorry? No, I'm not going into continuity and all these things. I'm just simply saying that if this, so you see, the thing is what he is saying, what I will do, I will just take
derivative of this function. Yes.
Derivative of this function, I will just evaluate at this, and that will give me the partial derivative of this at 0, 0. Okay, but what is the problem? It's basically this function and this function, they are not same in a open ball containing 0, 0. Okay, so that is the main issue.
Okay.
Pritam, you want to say something?
Sir, you just compared about two functions. Which one you said is not the same in the ball?
No, this function, and this function.
This is the same function, right?
Both are the same only, no, sir?
This is same only, no, sir?
No, they are not same. Okay, this is not defined.
Okay. At 0, 0.
Not defined at 0, 0. Okay, this function is defined at 0, 0. Okay, so if you evaluate 0, 0, then it's not defined. Okay. But this function, we have defined it as 0 at point 0, 0. Okay, so
which function, sir?
This f of x.
It is already defined at 0.
But yeah, so
then we have to
okay,
we have to calculate xy in the form so that the x is not in the lower part.
Yes.
when df by dx is there, and then similarly
Please.
y.
Okay, so like whoever is not talking, please mute yourself. I'm getting a lot of noises. Okay. Yes. Okay.
We have to that x square is there in the denominator. We have to eliminate that part.
Yeah. So the thing is, yeah.
So
the
that
thing,
when it becomes 0, it does not affect the
no,
calculation.
sorry, I didn't get it. Like, can you repeat what you were saying?
X square plus y square is there, na?
Yes.
We have to take out from the denominator.
Which one?
We have to calculate such a way that x square plus y square is not in the denominator part, so that we can put 0 for x.
No. That certainly you cannot do. See, since this function is not defined at 0, 0, that's why we have simply defined it as 0 at this point. Okay.
Sir, are we trying to define like g of x? It's through open ball concept that I am not understood, sir. Like
No.
how the open ball concept is related to into the partial derivative.
No, so okay, so actually he asked some question, like what he is asking. Okay, so basically, so this is my function, right?
Yes, sir. And what is the reason like you have taken as g of x? Like what we are want to conclude, sir, from it?
Just a minute, let me tell his question first. And it's 0 if this is the function, right? This is the given function. So what actually he was trying to say, like whether I can do in this way. I'll just take the partial derivative of x, this one, this part. Okay. Then I'll just evaluate that function at point 0, 0. So this will, so he is claiming that this should give me this one. So this will give me this one. So my point was this function at 0, 0, at 0, 0.
It's not defined.
This one is not same as this one.
Correct, sir.
So this part is not same as this one. Okay, so that's why you cannot do this trick.
Yes, sir, correct, sir. So my second question is that then if xy equal to 0, okay, then why we cannot say that if dash xy equal to 0 only, because it is its definition is 0 is there at value 0, it is already 0 is there.
No, then see the thing is, okay, so okay, basically what you are saying, okay, suppose, so see the thing is you have to know the value of the function in a neighborhood of that point, then only you can see. Suppose I am taking this function,
so that means it is a limit problem, and from the first definition of a partial derivative I need to solve it. There is no other way.
No, there is no other way. You have to go through the definition of the partial derivative.
Okay. Yes.
Okay. So I was trying to say that, okay, so you are actually differentiating a different function, okay, not the same function, because the value of the function at 0, 0 is 0. But what you are taking xy by x square plus y square. This is not the value of the function at 0, 0. The value of the function at 0 is 0. Okay.
Definition is different.
Yeah, they are certainly different, because see the value. So if I'll say that what is the value of this function at 0, 0, you are not going to tell me that the value of the function at 0, 0 is x square plus y square. This is not the value of the function at 0, 0. The value of the function at 0, 0 is 0. Okay, so they are two different things. Okay, so you cannot differentiate this function and put 0, 0 to get the partial derivative of the function at 0, 0. Okay, so you cannot do that, because this is a piecewise function. So in some different region you have different value. Okay, so you cannot take some value from a particular region and you cannot differentiate it, and you cannot put the value of some other region to say that in that other region that is the partial derivative of this function. Okay, so what you are taking the value in a different region, that is So excluding, so I'm excluding this origin. So you are taking the value in this region, but you are saying the difference. So, but you are saying I'll differentiate this one and I'll put this value to get the partial differentiation of this function at this point. Which is not true, because you are not considering the value of that function at that particular point. You are considering the value of the function at some different point. Okay.
So the given function is equal to 0 at 0, 0.
Yes, yes. This is how we
Also
define
0,
this.
right?
Sorry?
The derivative, partial derivative also will be 0.
Yeah, probably. Yeah, mostly it will be 0. Yeah.
So, sir, can I say that if there is an open ball, okay, actually is open wall is defined, then can I say that function is continuous around that point?
No, what do you mean by this? Open ball is defined like
Okay, so if I take a, suppose I take a 0.34, okay,
Sorry?
and take a 0.34 instead of 0, 0. Okay, I took a 0.34. Now this is the definition: xy by x square plus y square. Okay, now at this position, this is defined.
Yes,
okay,
then you can apply this rule, because see, in this, if you take the 0.34, if you take suppose 34, okay, basically you can get an open ball, right? Which certainly you can exclude 0, 0 from that ball, right? So in this open ball, the value of the function is 1, right?
Yes.
If you take any point in the open ball, then f of a comma b is nothing but ab by a square plus b square, right?
Yes, sir.
So then you can apply it. Okay, then you can take the partial derivative and you can substitute the value to get the partial derivative. Okay.
So then what is meant by the open ball exists? Is it means that at this open ball all the function points are defined, and is it the, can I say that it is continuous at 3, 4? Because everything is no, I cannot say that continuous. It is that only all the value exists.
So the thing is, see, that again I'm saying that when you are taking this one, for this point, okay, so basically you are taking a different thing. You are not taking the same thing, because so see, if when f of 0, 0, if simply you will substitute in this value, then you will, so this is not defined.
Yep, sir, you are right, sir, correct.
So when you are saying that I will just simply partial derivative this function with respect to x, then you are taking a completely different function. You are not taking the same function, because the value of this function at 0, 0 is 0.
Yes, sir, you are right, sir.
Yes.
Yes, you are right. So we need to go by the partial differential limit definition. Then
Yes,
this is the only choice. We have no other choice.
Yes. Okay.
And
so
yes.
Sir,
what is this open ball concept, sir? Like in partial derivatives, like what we are trying to extract from, like I didn't understand in the lecture also, sir, like the open ball concept.
No, the open ball, see, the thing is, okay, so see the concept of, you cannot talk about the concept of limit without a open ball. Okay, so whatever the limit, whatever you are talking, so you need a open ball. Okay, so basically the open ball is basically, it's a, so you have a point somewhere here. So open ball is basically, it's a circle, okay, containing that point. Okay. So so the thing is, so in the case of one variable, so what you have in the concept of in case of one variable, instead of open ball you have an interval, right?
Yeah. So is it related to left limit and right limit? Are we checking? And
yes, that is what, because see,
okay,
so you need to, so the thing is what, you have to come to this point from left hand side and from the right hand side. Okay, so what you want all these points to be inside your domain of f, right? So when you are approaching to this point from the left hand side and from the right hand side, okay, suppose this is your point. So when you are approaching to this point, so you need all this point inside this interval to to be a part of your domain of F.
Yeah, yeah.
So
Yes.
that's why you need the concept of open ball. So otherwise, how you'll come to that point? Okay, so how you'll discuss about the how
Okay.
you'll take the limit? Okay, so how you'll get a sequence so that it will come towards A. Okay, if there is no open ball containing that point.
So open world concept come into like the multivariable functions.
So here actually you have in case of R you have only two things, right? You have left hand side and right hand side. That's why here the open ball is nothing but an interval.
Okay, okay.
Okay. But here the open ball is nothing but a circle. Okay.
So then what about 3-dimension and more?
Sorry.
What about 3-dimension and
Then
more?
similarly, like you will get some kind of sphere.
Sphere, right?
Yes. Sphere, like similarly for 4-dimension, you will get something else. Okay. So basically, open ball is more or less this one. This maybe say x1 a1 square less than some number. So yeah, so in case of when basically your n is 1, then you will get an interval, and if n is 2, then you will get a sphere, circle, and if n is 3, then you will get sphere, and n is 4, then you will get something. Okay.
What is A? A is the center point.
Yeah, so basically it's a center point. Yeah, so here this is A, right? So when I'm saying
Center point of what, sir?
that open ball.
Okay.
So in two R2 you will have the first two terms.
Yes. I'll have only these two things.
Then
So,
A1, A2 are
it's a point in R2, right? A1 and A2.
Okay. There is no center point here.
No, here the center point is A1, A2, AN, right? This is the center point. See how you represent a circle.
So this would be in Rn the coordinate of the center point, right?
See how you see this is a point in circle in R square. How you what is the equation of the circle? And the center of the circle is A1 and A2. What is that equation? This one, right? Ax1 square.
Yeah.
R, right? So where are it something positive? Yes. Okay. So what open ball means? We are considering all the points inside the circle. Okay. So that's why we can take this symbol. Okay. Obviously, we are excluding the boundary of that point.
This is less than n, right, sir?
Sorry?
Less than n. Less than n.
N.
Yes.
That is R.
This is
R.
Yeah.
Radius.
Radius of the circle.
So is it x minus a1 square plus y minus a2 square? No? Looks up. Right.
Okay. So do you want me to discuss this one to solve this question?
Yeah, please.
Okay.
At 0, how to find?
Okay, so
but straight away we cannot say df by dx is 0 because
no, we can't because that is the issue. Like how you'll say it?
Because the function is 0, it's a constant.
No, the constant only see the thing is okay. So if I take this function, let's say, say it's basically half at half, okay, and 0 for other points, okay. So what will be the differentiates the derivative of this function at half?
0.
No, it's not differentiable at half. Okay, so the function is itself is not differentiable at half. So if you just simply take the value of that function, okay, and if you differentiate it, then obviously every time you will get the derivative to be 0.
Yeah.
So how you
Sir,
can,
is it because it's not continuous?
sorry?
Is it because fx is not continuous at half?
No. It's not about continuity. It's basically you cannot see. The thing is, what he is saying, this is x. So now if you take the value of f of 1 and you will take, so you will get e. So now if you differentiate this thing, then you will get 0. So,
Yes,
so basically when you are taking f of 1 and you are differentiating, then basically you are differentiating a different thing. Okay, this is a different function. This is, so you are, this is, so if this is a constant function. Okay, so this is a something else. Okay, you have to differentiate the given function. So when you are evaluating that function, so you are basically getting the value of the function at a single point. You are not differentiating that function. You are just differentiating a scalar. Okay, so they are completely different things. So I have to differentiate this one. Okay, so by your logic, if I'll differentiate the value of the function, the value is basically is always a scalar. So I will always get 0.
But f of x at xy at 0, 0 is given as a function 0 or value 0? How to interpret that?
No, this is a value, right?
That can be seen as a function also, right?
No, so that is the problem, like that is the main problem here. So the thing is, what you are, see, you are differentiating a value, you are not differentiating a function. Okay, so when you are taking the particular value and you are trying to differentiate it, okay, then you are differentiating a value of a function. Okay, that is basically scalar. You are not differentiating that function.
No, just for understanding,
yes.
If I have to, first I have to look at whether at that specific point the function is differentiable or not.
Yes.
If it is differentiable, then what is the value? That is what I have to look at. For that, I have to look at the left hand limit equal to right hand limit is equal to the value at that specific point. Then only it is differentiable, right?
No, that is the definition of continuity.
Okay, so maybe then we can just go ahead with this specific problem solution approach. Maybe that will make it a little clear.
Okay.
Sir, sorry for disturbance, sir. Can you go to the just top? A small doubt is there.
Just a minute. Yes.
Sir, yeah, so you have written a problem that says that fx is equal to half at x equal to half. Sir, how you can prove that I cannot derivative this function at x?
Yeah, you try to go back and see the lecture of one variable calculus. Okay.
Okay.
That
okay, so the normal derivative definition.
Yes.
It is continuous or not.
This is first of all, this is not continuous.
Yes.
Because the left hand limit is 0.
And right hand limit is 0.
And this is not same as the value of the function. Okay.
Yep. So that is the reason it is not derivative. So is this same definition exist for the partial derivative?
Yeah, that is what the definition in one variable calculus and the definition in two variable calculus, they are the same, right? There is no much difference in the definition.
Okay, sir.
Yeah, so basically we are going through the same definition, no difference.
Okay.
Okay, so now what you want to compute? You want to compute the partial derivative of this function with at the point x at origin. So by definition, what is that? Limit s tends to 0 f of x naught y naught. So here x naught and y naught, that is basically 0, 0. plus h times 1, 0. So what will be this value?
So 1 not 0 from where it come? 1 0 h.
This is the definition, right? This we are taking the partial derivative with respect to x.
Okay.
So you have to take the unit vector in the direction of x-axis. This is the unit vector, right?
Okay. So the definition it is written as if x plus h comma 0. So you
Yeah,
just
that is basically the same thing. Okay, so
okay, sir, got it.
okay, like better I should change it to 0 plus h comma 0. Okay.
So this h0 minus f of 0, 0 by h.
So what is f of h comma 0?
That is xy by h square plus y square.
This is what?
H
times 0 by h square plus 0 square. And this is by definition it's 0. And this is also 0. So that means this is 0 by 0 divided by h. And this is nothing but 0.
But if h tends to 0, then denominator becomes 0, right?
Sorry?
If h tends to 0 means denominator also becomes 0. Then again undefined. It is not undefined.
No. It's not equal to. It tends to.
So it tends to 0. See, the thing is, okay.
Okay.
So the thing is, so let's say h equal to, you are taking h equal to the sequence hn 1 by n, right? So this sequence converges to 0. Okay. So now if you take, so when your h1 is equal to 1, okay, so just treat this as a value of, as a function of f of h. Okay. So what is this? This is 0 minus 0 by 1, which is 0. Okay. So then if you take 2, then also you'll get 0. Okay. So as h of n tends to 0, okay, so basically f of s also tends to 0. Okay. So you cannot substitute the value of value of s to be 0, and so if you do that, then certainly it's not defined. But that is not the definition of limit. Okay. So you need to calculate the value of the function f of s when h tends to 0. Okay. So when h tends to 0, then f of s basically it's basically tends to 0. Okay. If you take some non-zero number that tends to 0, then for all the non-zero number, f of h is basically 0. Okay. So that's why the partial derivative of f with respect to x at the point 0, 0 is 0. And similarly, you can compute that the partial derivative of f with respect to y at point 0, 0 is also 0.
So is there any other function where it is defined 0 or some other value, but the derivative is not 0?
Sorry?
In this case, the f of x was defined as 0, and the partial derivative is also 0. Is there other function where if the function is 0, but the partial derivative is not 0?
I guess that is possible. But yeah, I guess that is possible. But yeah, we have to think about it, whether they like how we can construct that function.
So how it can be understood, like using the open ball, you can explain something for such.
Sorry.
Using the open ball, can you explain for such function what is the difference? How it will?
No, actually, see, the thing is, the partial derivative, you are just taking the rate of change of the function with respect in the direction of x-axis, right?
Correct.
So it doesn't matter what is the value of that function at that point, at that particular point. You see, the thing is, what you are doing, you are checking the change of the value of the function at that point, right? So
okay.
So basically, so basically what you are taking, so what is this? So, okay, so you have this 0 0 over here, and this is, let's say, this is the image of the function at this is f of 0 0. Okay, this is the image of the function. So this is 0 0. So what actually you are taking? You are basically you are trying to find the slope of this line. Okay, so it doesn't matter what is the value of it. It's basically the behavior of the function in this neighborhood. Okay, in this open ball, like if you take some open ball, you just need to check the behavior of the function. So according to the behavior of the function, you will get the tangent line.
Okay.
So it's basically, it doesn't matter, like so as you said, whether there is some function where the value of the function at 0 0 is 0, but the partial derivative is something different. That is certainly possible. Okay, it's
So
not like that. So it's not like that. If the value of the function at 0 0 is 0, that doesn't imply that the derivative of the function at that point is 0.
Okay, understood.
Okay, so let's come to the
Does
limit.
it mean that any piecewise function we have to always go through that fundamental definition only?
Sorry?
For any piecewise function.
Yes. You have to go that way. Okay. It's depend. Actually, if you are calculating the derivative of the function in the boundary, okay, then you have to go by that fundamental rule. Okay.
Yeah, it's in the boundary. I agree. So if the differential is within a area, within a range where it is clearly defined, then there is no issue. There is no piecewise there. Only boundary. Only.
Yes.
Okay.
For example, Mohan, like if you take this function, f of x is equal to 2x. So here actually what is the value of the function at 0? It's 0, right?
Correct.
But the derivative is not 0, right?
Yeah.
But okay, so for two variable, I have to think about it little more. Okay, how I can construct that function where the partial derivative is. But okay, yes.
I think the numerator, if it is the plus function, then it will come.
Yeah, probably. Yeah.
So if we take the same function but change the numerator by from xy to x square, then I think it would work.
So you are saying for this function, if you
it's
down, which one?
Yes, sir. For this function, instead of xy, if we have x square, then it will work, I think.
X square. Yeah, sure. Because this is this you will get this will get x square. This will get I guess you have to take x cube, because if this is h square, so this will be your h, this will be your 1, right, Pritam?
Yes, sir.
So then basically this is 1 minus 0 by h. Okay, so this doesn't exist, but okay, your guess is correct. Instead of x square, if we take x cube, then you will get 0.
Yes,
okay.
Sir.
Yeah.
It will get 0.
Yes. Just let me do it. what actually Pritham is saying. So if you take this function, and this is x cube square, if x and y are non-zero, and this is 0, this is 0, then if you take the partial derivative of this function at the point 0, 0, and this is by definition so what is this value?
1 h is
This is h, right?
h, yeah.
This is 0, right? So this is nothing but limit
H cube by h square, h, yeah.
So this is h by h, so this is nothing but 1.
Yeah, yeah. If
So,
it h square, what happens? You said
which one?
Square.
This one.
X square in the
X square.
Ah.
X square, then partial derivative doesn't exist at 0, 0.
Because it will become 1, 0.
Yeah. So this is 1, right? If I'll change the function from x cube to x square, this is 1, right?
Yes.
Then I will get 1 by h, right?
Yeah, 1 by h.
But this limit doesn't exist, right?
Now, how you will get 1 by h?
No, what is a so
yeah 1, yes, correct
1 by h. So then this limit doesn't exist, right?
Is it 1 by h tends to 0? It is 1 only, no?
No. How come? Like if h tends to 0, then 1 by h
is 1, right? The denominator becomes very small, then therefore it is 1.
No, if denominator
becomes infinite.
is very small, then if you have a number, big number here, and you have a small number here, okay, then you will get something bigger, right?
Yeah, sorry.
So for example, if you take hn is equal to 1 by n, then what will be the value of 1 by hn?
Sorry. Yes.
This is n, right? So as hn tends to 0, this basically this diverges to infinite.
Right? It doesn't exist.
Yeah. So the limit doesn't.
Just one point on the previous line that is there, wherein we are saying that limit h change to 0, 1 by h. No. Over here only. Yeah, this line itself. So this one refers to only right hand limit, right? Or this refers to left hand? Yeah.
See, it really doesn't matter. If one of them doesn't exist, then suddenly limit doesn't exist. Okay. So, right?
Sir, x cube, when you took, you said h, it should be 2h, na, sir? When you took x cube.
Which
3h.
one?
X cube, when you took, it's f h comma 0, function of h. What is the value?
Yeah, x cube.
This is what?
3h, na, sir?
No. What is f of h comma 0? What is f of h comma 0?
H cube by h square.
This is h cube
by
h square plus 0, right? What is this? This is h, right?
It will be. H.
Yes.
Okay.
So this is where my point was. This is a right hand side x cube. Let's keep it x cube only. And right hand limit, yeah, it is coming h by h equal to 1. But when I'm keeping it f of x minus left hand limit, then numerator is coming what? Numerator is coming minus h, isn't it? Because
no, why?
Minus...
So when you will take the right, so when you are taking left hand limit, okay, this is negative and this is negative, right? So both the negative sign will get cancelled, right? So eventually you will get positive, right?
Is it? I thought h itself is positive. It is just that we say 0 minus h, just delta negative from the position where I want to do differentiation, right?
No.
Do
sorry,
I not do? How do I? Definition is what? If I just single variable, or if I do it, the definition is if I have to do it on right hand side limit, it would be f of x plus h minus fx divided by h. And when I'm going to do it on the left hand side, it would be f of x minus h minus f of x divided by h. So h as a concept is a positive number itself. Delta h.
No, it's okay. So you can actually interchange the things. Okay, whatever you are saying is correct. That when you are talking about that definition, okay. So this let's say x minus h
minus f of x divided by h. This is my left hand limit.
Left hand limit, right?
Right hand would be f of x plus h. Just x plus h will happen. That's it.
Okay, so okay, let me what
I thought that left hand limit is coming as -1 and right hand limit is coming
okay.
1.
So the thing is, okay, just let me write what you are saying. So okay, so the thing is, so you are saying you want s to be positive, right?
Yeah.
So okay, I can write it as this, right? Limit. So here my s are negative, but instead of that, I will write x plus h.
Okay.
So they are the same thing, right? So here I am taking h to be positive, here I am taking h to be negative. Okay, so eventually this x plus h and x minus a will give me the same thing, right? See, here you are taking s to be half, and here you are taking s to be minus half. Okay, so then x minus half. So here you are getting x minus half. Okay, and here also you are getting x minus half. Right, so you are getting the same thing. You can change it.
No, where I'm coming, if I may just go to the x cube definition of fx. Therein I was just thinking that if I keep it like this, then it was coming -1. Is it coming like that, or am I doing
no? You are making mistakes. See, this is s by h, so this is 1. Okay, first of all. Okay, so then whatever you will take, you will get 1. Okay, whatever sequence you are going to take.
So what he was telling is, if minus h comes, then it will be minus h cube by h square.
Yes, he is saying that, okay, we are computing this thing. H tends to 0, h by h. Okay, so
this
no, it is not coming h by h. Negative.
No,
left hand side is coming minus h by h.
No. See, this is the limit, right? So finally you want to compute this one, right? You want to compute this one, right?
I am coming to this from the basic definition, 2 step down the line. I am coming to this intermediate step. I'm saying that basic definition itself from f of h is 0. What we have put it.
This is basically h by h, right? I'm this equality, whatever I have written here, this is basically h by h.
This is h by h. What he's saying is f of minus h 0. That function he's saying.
No. He is saying that if you compute the left hand limit of this function, and if we compute the right hand limit of this function, he is saying I will get some different thing.
Yeah, he said left hand function it would be f of minus h comma 0.
Which one? Okay, so let me do it. Okay. So okay, so you okay? Just let me. Okay, one more thing I will suggest.
Can we proceed to the next example? Maybe later on we can address it.
Yeah, fine. Okay, so okay, so one thing I will suggest. Okay, if possible, please go and revisit the calculus 1 things. Okay, so again, like whatever you are saying here, actually, if you so you want to take the left hand limit and right hand limit of this function. Okay, that is what you want to do, right, Ranjit?
Yeah.
So okay, so one thing I'll do it. Basically, you will get the same thing. Okay.
Okay. We will
Sir, in
take it up later.
the denominator will also become minus h.
Yes,
because
yes,
we will
yes.
do 0 minus h. So that will be remain. It will come. The answer will be the same.
Yeah. Basically, you will get the same thing. Yeah. Okay, so So let's do some limit. Okay, so okay, so so the problem here, calculating the limit of multivariable function is little tricky. So what is the reason behind that? So so when you
So will you discuss about the directional derivatives?
Sorry, no. I'll discuss directional derivative in the next session. Okay, so let me discuss.
Can you show the question?
Because I want to discuss, I want to do directional derivative and gradient at the same time. So because if you do the directional derivative by
Sir,
using
can you show the question, sir?
Using the definition, then you have to do a lot of calculations. So if you do using the concept of gradient, then you can do it easily. Okay, so that's why I want to do this directional derivative and gradient at the same time. Okay.
Yes, sir. Okay.
Okay, so this is the question. Okay, but okay, this is basically, it's not a question, it's basically the definition or some of the properties of limit. So the problem with the concept of limit over here, so when we have one variable calculus, okay, so in one variable calculus, in generally we do deal with function from R to R. So this is my domain. This is my real line. This is my domain of. This is domain of. So when actually we talk about the limit, so the only thing we need to compute. So we need to compute two finite things. Okay. So not finite things. We can compute the limit using some finite methods. That is the right hand limit, the left hand limit. Okay. So because in R square, you have only two different directions. That is, one is this left hand side and another one is, one is left hand side and another one is right hand side. So once you compute the left hand limit and once you compute the right hand limit, and once you compute that, then you can say that whether that limit exists or not. Okay, if they are certainly equal, then if the left hand limit and right hand limit are equal, then you can say that the limit of the function exists at that point, and whatever the value will get, that will be the limit of the function. Okay, so that is the thing you do when you have a function from R to R. Okay, the problem occurs when you have a function from R2 to R. So now the domain is R square, means you have a plane, right? This is a domain. Now, so if you have a point here, so now we don't have the concept of left hand limit and the right hand limit. We have many different limits because I can reach to this point through infinitely many directions. I can come to this point from this side. I can come to this point from this side. So I can come to this point from this side. I can come to this point from this side. So I can come to that point using infinitely many directions. Okay. So basically that is the difficulty when you are dealing with limits for the function of two variables. Okay. So basically to show that limit doesn't exist. So what basically we do in the case of one variable, which to show that limit doesn't exist, we compute left hand limit and we compute right hand limit. If they are not equal, then we can say that the limit doesn't exist. So in the case of infinite, in case of more than one variable, so basically for I'm talking about only in case of R2. So if you can show that, okay, I have one direction over here and I have one direction over here, and so in this direction the limit is L, and using from this direction the limit is M, and if L is not equal to M, then I can say that limit doesn't exist. So if the limit is different for at least two different directions, then you can say that the limit doesn't exist. But proving limit exists is basically it's difficult, because you have to make sure that the limit in value is same for all the possible directions. For all the possible direction, you have to make sure that the limit exists are same.
Sir, then how to find out total number of directions? Like
Sorry.
Then how to find out total number of directions? Like you were saying that
no, there are infinitely many directions. That is why it's difficult. There is no particular method to find the limit of multivariable functions. Okay, there is no method. Okay, either you have to do it some mathematical proof. Okay, that limit exists. So you by checking the limits of directions, different direction, you cannot say that the limit exists, because there are infinitely many directions. Okay, so basically
how to confirm continuity, sir?
Yeah, that is for some easy function. Actually, we can do that, but if the function is slightly complicated, then it's really difficult to find out the limits. Okay, it's difficult. Okay, so even like there are few functions, like even some nice functions also, it's really difficult to say whether the limit exists or not.
But sir, like during lecture, sir, whatever examples a professor has discussed, right? So he was taking a particular point, right? And then he was exploring the limit around that point.
Even for a particular point also, that is difficult. Okay. Whatever function he took, they are slightly simpler. Yeah.
Okay, so he had not taken many directions, sir. Professor has taken only like those 2 points, and then he had computed the value of the limit, and then accordingly we have taken a call that whether limit exists or limit does not exist, right?
No.
I think he considered y equal to mx plus c.
No. Correct. Y equal to x one line, and then y equal to mx plus c.
Right? No.
Consider all lines, right?
Yeah. So whenever he considered y equal to mx, so during using that, he disproved that the limit doesn't exist. Okay. So to show that limit doesn't exist, you just have to take two different directions for which the limits are different. Okay. To prove, I am saying to prove limit exists. Okay, you have to make sure that the limiting value is same for all the possible directions. Okay, see, to prove limit doesn't exist, it's slightly easier than to prove limit exists. Okay.
So if you take y equal to mx, and then if it becomes a constant, then it exists, right?
No, y equal to mx.
And then if that limit is value is constant without m coming into the picture.
No, sorry, I didn't get your question. Like you are so. I'll come to few questions and I'll try to discuss. So when you were taking y equal to mx, then this is a direction. Okay. This is a direction, right? So what is means? So suppose you are talking about you want to compute the limit of the function at 0, 0, right? So if you take y equal to x, so this line.
Yes.
So now you are talking about the limit of the function in this direction when you are coming to 0, 0 using this line. Okay. So when you are coming to this point using this line, you will get some limit. You will get some value. Okay.
Yeah.
If you take some other line, maybe say y equal to 2x. So this will be a different line from the previous one, right? So you'll get something like this. Okay. So when you'll come to 0, 0 using this line, y equal to 2x, y equal to x, then you'll get some different limit. You will get some limit. Let's say, okay. So one thing is, if L is not equal to m, then directly you can say that limit doesn't exist.
Correct.
But to prove that limit doesn't exist, so the problem is if L is equals to M, okay, then you cannot say that limit exists.
So in this case, when the example of if y equal to mx is taken, in mx form it is taken, and if the result does not include m in it, the variable m in it,
still you
it
cannot
be a constant, right? Then all direction will be same constant.
No, then still you are excluding few paths. You are now, see,
excluding y-axis.
Not y-axis. See, the problem is, okay, so the problem is it's not like you have to always come through a line. You can come like this.
Okay. Curve also, parabola also.
You can come using a curve. You can come using a curve. Okay, so parabola is more or less a curve. Okay, so you can come in this way. Okay, so there is no it's not like that you have to consider line. Okay.
Well-defined path.
Yeah, basically you have to consider all the different paths. Okay, certainly lines are also paths, but these are not the only paths. Okay, you can
this will help only in disproving something, that's all.
Exactly, this will help you only disproving something. Okay, so again I'm saying that proving limit exists is difficult. Okay, so you actually it's really difficult to prove whether the limit exist or not. There are few methods, okay, but yeah, also like there are function where you cannot apply these methods.
So
yes.
So when professor says nice functions, what does he mean?
Nice function means mostly it's I guess it's differentiable.
Okay, sir.
Probably we'll see. Sometimes I guess continuity is also enough. Okay. You'll see next week. Probably in gradient, I guess, because actually he's basically saying all the partial derivative are continuous, right?
Yes, sir.
So that is more or less equivalent to the fact that the function is differentiable. Okay.
Okay.
But anyway, I don't. So anyway, will not discuss differentiability in this course. That is much more complicated than all these things. Okay, that is really complicated.
Except for single variable, we had discussed differentiability, right?
Yeah. For single variable, you have the, but okay, for multivariable calculus, the differentiability is there is a huge difference in the differentiability what you have seen in the single variable. In they are same, but the approach is completely different. So
most of the cases will be multivariable only.
No, you are not going to deal with the differentiability. Okay, basically, so the main thing is you need to see the main idea of machine learning. You need to find the value of maxima minima of a multivariable function. Okay, for that you just need this this partial differentiation.
Okay.
So in this, all options are correct except 3.
Yes, true. Okay, so the point is actually why actually I have included this question. Okay, so the point is the properties of the limits of a multivariable function is basically the same what you have studied in case of one variable function. Okay, so similarly, so the thing is you have studied in the one variable function, right? So limit x tends to a f of x plus g of x.
You can apply the limit separately.
Yes, separately. So provided that both the limit exist. Okay. So similarly, you can take the product. Okay. So okay. You actually So these are really helpful properties. Like you can actually apply it to get limit of maybe some complicated function. Okay. And similarly, you can so in case of one variable, we have also limit x tends to a g of x.
Again, limit theorem.
Yes. And similarly, we have similar kind of property in case of multivariable function. Okay. And also, if the limit of x tends to a, g of x is non-zero, then I can apply this quotient rule that limit x tends to a, f of x by g of x is limit x tends to a, f of x by limit x tends to a, g of x. And similarly, I have this property for multivariable function.
Shouldn't we mention fourth one that g of xy should not be?
The third one is wrong, right?
Yeah, third one is wrong.
Fourth one.
But you
Why the third one is wrong?
it is equal to 5L.
It should be equal.
Yes, it should be equal
Because
to 5L.
so similarly, like you have some property, right? In case of one variable, x tends to a c of f of x is nothing but c times limit x tends to a f of x, right? So this property is also true for multivariable function. Okay, but here actually in third option, it's saying that this limit is not equal to 5 times the limit of f of x comma y.
In the fourth option, g of xy should be mentioned, right? Since it's the quotient.
Sorry.
The quotient rule, g of xy, that not mentioned, no?
Yeah, that is basically, this is mentioned L, right? This is k. Okay. So what is this? This is L by k, right?
G of xy is
what is L? L is given here, right?
That is k, right?
Sorry?
So in the fourth option, which is the quotient
Okay, sorry, I'm saying it again. Okay, so the thing is, I'm having difficulty to understand what you are saying. It's better if you say loudly. Okay.
So what I'm saying is, hello.
Huh.
Are you hear me? I'm audible.
Yes. Huh.
What I was saying is the quotient rule, the fourth one, it says that g of xy. So should it be mentioned that now g of xy should not tend to 0, right?
Yeah, this k is 0. It's mentioned, right? See what is this? So we have mentioned that limit. So what the only condition we need that this value is not 0. This value is not 0. Okay. Which we have mentioned here. Right. This k is not 0. So what is k? K is basically this limit, right?
Okay.
So that is already mentioned. Okay.
Okay.
Yeah. Okay, so now okay, so what will be the value of this limit? So the first thing is
we can substitute directly.
Yes, you can do it, but not for all the cases, but in this case certainly you can. So what is this? This is so if you go to the previous thing, So this f, this is g. Okay, so this one is f of xy, this one is g of xy. To apply this quotient rule, we have to make sure that this limit xy tends to 2, xy tends to 2, 3, g of xy, this is
Not equal to 0.
Not equal to 0. Okay, that is what we need to apply this quotient.
Numerator is 10.
Yes, true. So so this limit is, I guess, 2 square plus 3 square minus 3.
2.
This is 8, right?
10,
sir.
Okay.
Okay,
Okay, 10.
Denominator is 5.
Yeah, numerator is 5.
Y square minus x square is 5.
Yes, sir.
So then if you apply the quotient rule, what you will get? 10 by 5,
2.
which is 2. Okay, so
the limit is 2, sir, right?
Yes, then the limit is 2. Yeah. So the only thing you need that to apply this limit, you just need to know that whether this part is 0 or not. So since this limit is non-zero, then we can apply this rule. Okay,
That
this
becomes 0, then whole story changes.
Yeah, so no, if that is 0, then basically you cannot apply that rule. Okay.
If we cannot apply the values directly, is there an example where we cannot apply directly the values? We have to differentiate and then apply or something like that?
No, for example, if you take maybe say x minus y, x square minus y square by x plus y. Okay. So in this case, you cannot apply directly the value.
So how do you approach this?
No, sir. Here I can apply, no, sir. Value of x and y is 2, 3.
No.
Sorry, how you will apply?
No, then now can't apply. Yes.
Yeah, you cannot apply because this is 0. Okay.
Yes. Now I can't apply. Yes.
So how do you approach this? We have to.
Okay, like the thing is, okay, you have to check after that.
So here you simplify, cancel expression.
Yeah. So then you have to make sure whether first you have to check whether you can cancel something. Okay. So the
Is
thing.
there anything similar to L'Hopital rule here?
Sorry.
Is there anything similar to L'Hopital rule here?
No. Okay, there is one L'Hopital rule in case of 2 variable, but that is slightly complicated. Okay, but yeah.
Okay.
No, you can apply a L'Hopital rule once you convert a function of 2 variable to 1 variable. Otherwise, you can't. Now this is a function of 2 variable. You cannot apply the L'Hopital rule given in function of 1 variable. Okay, this is basically x minus. Now actually you can cancel this thing. Okay.
Okay.
Then what you are getting? You are basically getting x minus 1, which is
0.
So you have to check actually. Not all the time you can actually cancel. Okay, so
if it's not cancelled, then you have still an approach. Like
probably you have to use some different approach. Okay. Yeah, so certainly there is not a single approach through which you can deal all the possible cases. Okay, so so now actually we are maybe in a position where the limit exists. So okay, so here I want to show that I want to find the limit of this function. Okay, so the next thing. Okay, so how actually in most of the cases how you can say that the limit actually exists. So it's not true in general, but I guess it's true for most of the cases. So here if you see this degree of the below polynomial, it's actually 2.
Okay.
Okay, it's and if you see the degree of the above polynomial, okay, it's basically 4. So the degree, if the degree of the above one is greater than the degree of the below one, in that cases you can expect the limit, you should get some limit. Okay. Otherwise, if the degree are same, then most of the cases you won't get any limit. Okay.
That's a thumb rule.
Sorry.
That's a thumb rule kind of thing.
Yes, true. But I don't think it's true in general. Okay.
Okay.
But I guess in most of the cases, like if you have polynomial in both numerator and denominator, then in that case, I guess you can expect this result.
But what is the conceptual connection there too?
Sorry?
What is the conceptual connection of this degree with the eventual limit being there or not?
No, the thing is, if the degree if this degree is 0, then this goes to 0. Sorry, this goes to 0 much more faster than the below. Okay. So that is why you can expect that when you will compute the limit at 0, this will go to 0. Okay, because this numerator goes to 0 much more faster than the denominator. Okay, that is how you can that's why you can expect that when the degree of the above one is less than the degree of greater than the degree of the below one, then most likely the limit of the function at that point will be 0. At 0, 0 is 0. Okay. For example, what I was trying to say, this x3, and you have something, say, x square. Okay, so if x is small, right, x is in between 0 to 1, then certainly x cube is less than x square, right? So in some sense, x3 goes faster to 0 than x square. Okay, so now I want to prove that this limit exists.
Okay.
So the thing is, I'm just going to give you one approach. Okay, it's not like that using that approach you can solve all the questions. Okay, so as I mentioned it earlier, there is no finite methods through which you can prove that the limit exists. Okay, so for different problem you have to apply different methods. Okay. Okay, so the first thing is, so we want a term, something called this. Right. So the first thing what we'll do now, we know that x square is always greater than 0. And it's less than, right?
Yeah.
So now if I divide by x square plus y square, okay. So if I divide x square by y square, because x square plus y square is also positive, so obviously you will get the same inequality.
So this is 1.
Then what I will get now?
Less
I'll
than
get
1.
0. Yeah, 0. right? But so what I want, so now what I have
4x square.
4x square.
So what I have to do now, I have to multiply 4y square, right?
Yeah.
So again 4y square is also positive. So if I multiply on both the sides, then actually I'll get the same inequality, right?
Yeah, limit is less than 4y square. Your 4y square should come in the numerator, right? In the middle term.
Okay, sorry. Yeah, true. Yes. So now I have my function. Okay.
So our limit is less than 4y square.
So now I have this inequality. So now if I apply this limit,
Where you will apply this?
Sorry.
Yeah. Okay. Yes. So the limit of right side will get 0. Therefore, you conclude the center limit is 0.
Exactly. So this is 0. This is 0. Okay. And that's why this limit is 0. Okay. So this is actually this is one of the method. So actually in most of the question, whatever we'll give you in this course, actually you can solve not most of the question, I guess all the question you can solve using this method. Okay. To show that limit exists.
If there is.
So as I said, there are huge number of methods through which you can solve, but you can show whether the limit exists or not. Maybe some Cartesian methods are there, but this is the one and only method through which you can, in this course, you can show that the limit exists. Okay. Okay, so then the limit of this function is basically 0.
So this was for one part, no?
Sorry?
This was when hello, sir, am I audible?
Yes.
I think it's a piecemeal function, no?
So
was it for both the parts or it was only for one part? Sorry, I had lost my connection in between. So, so this whatever technique you have presented, so that was for whole function or it was for one part, only the first part, like when...
No, I'm not talking about continuity. Maybe I'm not talking about partial differentiation. I'm just talking about the limit.
Okay.
Sir, here how to say that this is continuous at 0, 0?
No, the only thing you have to check that whether the limit of this function matches with the value of the function.
Okay, so now limit of the function is 0.
Yes,
right?
yes.
And the value of the function at 0, 0 is 0. So it means it is continuous.
Yes, if the limit of the function is same as the value of that function at that point, maybe say if the value of the is same as f of 0, 0, then you can say that f is continuous. Whatever, like the definition you have in the case of one variable, the same definition. Okay, if the limiting value is same as the value of the function at that point, then this function is continuous. Okay. See, the thing is, see why actually I don't have to care about when I'm talking about limit, why I don't have to care about this part. Can one of you tell me? No, while computing the limit, so why I don't have to care about this thing.
Because while we are taking the limit, xy is never actually at the point 0. It is always approaching 0, 0.
Exactly, because what we're taking xy tends to 0. Okay, so when actually, so basically what we're taking bunch of non-zero number approaching to 0, and when x and y are non-zero, at that time my value of the function is this. Okay, not this. So that's why I have only taken this one. Okay, because what I'm doing, I'm taking, so here when I'm saying that x, y and y, x and y are converging to 0, so basically I'm taking some non-zero number converging to 0. So when x and y are non-zero, then the value of the function is this one. Okay, so I really don't care what is the value of the function at that point. Okay, so like in the case of one variable, the limit of the function doesn't depend on the value of the function. Okay.
Sir, I have a confusion.
Sir, just a small. Yeah, sorry. Okay, please go ahead. Please go ahead. Okay.
When you say x comma y not equals to 0, does it mean both not equals to 0, or any one of them can be 0?
Sorry.
If you look at the first equation, it says x comma y not equals to 0. Does it mean that both are not equals to 0, or x or any of x or y can be 0?
Any, and like I'm saying both of them are not 0. Yeah.
0 or 0 comma 4?
Yes, you can.
That's the first expression, right?
Yeah. Certainly, if one of them is non-zero, then you are coming back to the first expression. Okay. And also, if you take, so in the meantime, so the thing is, in the meantime, even if you consider 0, 0 also, that is also not a problem, because f of 0, 0 is 0. Okay. So in that case, also you will get this equality.
Just
but in case 1 is 0, xy is multiplication is there, so automatically numerator will become 0, so limit will come to 0.
No, by definition, f of 0 is 0, 0. Okay.
So just a small doubt, sir. When x and y is 0, sir, then the expression is becoming 0 by 0 case, no, sir?
No, not expression. This one. Okay, I'm talking about this one. Okay. So why actually I'm taking this one, f of xy. Okay.
So it is not becoming a case of 0 by 0, sir?
No, when your xy is 0, 0, okay, what is the value of the function at 0, 0?
0.
So then you will get 0, right? So it's not an issue.
Okay, it's not an issue. Okay.
I'm just
a clarification. If the value of a function could not have been defined, then it could have been a case of a 0 by 0, right?
Yeah. Then it's problematic.
Then it could have been a case of 0 by 0, right?
Yes. But here actually the value of the function is 0.
Okay.
Okay, so this is actually, so here I actually proved that limit exists. As I said, this is probably the one approach through which you can solve almost all the questions. Not almost all, I guess all the questions.
For existing limits.
Yeah, for existing limit. To disprove limit, basically you can actually, for almost all the question, you can solve it using this. Okay, so the next question is, consider this function. So this is the function. So it's saying if f of x approaches to approaches to L as f of x approaches to the origin along y axis, then find the value of L. So So it's basically saying, this is your domain of A. Okay, this is your domain of A.
Sir, if you use the previous approach, then this limit will become again 0 to 0 or no?
No, you cannot apply the previous approach. Do you
Why
think
not?
now? Do you think now you can apply the previous approach?
Degree is same, huh?
No. Okay. So just okay. Then you start explaining your procedure. Okay. So then I can point it out where actually you are doing the mistake. So
X is less than x square plus y square.
Why?
No, x will be less than x square
No,
plus y
that is the problem. That is not true.
Why not? Because x square will be less than 1.
So you take 0.2.
Okay.
0, this point.
Wow.
If you apply this one over here, does it hold?
Doesn't hold.
Yeah. So that is not true. Okay. So that's why actually you cannot apply the same.
So might try using arithmetic mean and geometric mean over here.
Yes, please.
Arithmetic mean and geometric mean inequality may be used.
You cannot use it. Actually, the limit doesn't exist. Okay. So then you cannot use it. If you are using something and using that you are showing that limit exists, then there is some mistake in that process. Okay.
Okay.
So here limit doesn't exist. Okay. So it's saying that if you come to this origin, so the first question is saying, if you come to origin along this y-axis, then what will be the value of? So if you are coming to origin along y-axis, then where f of x comma y approaches. Okay.
Here L is the limit?
No, L is the limit when you are coming to origin along y-axis. Okay. When you are coming to origin along y-axis. Okay. So in that case, you have to find the limit. Okay. But you don't know what will be the value if you come along this path. Okay. It's basically it's asking you find the limit of the function when you are coming to origin along this line y-axis.
Okay.
You don't know what will be the value of the limit if you come along x-axis or maybe some y equal to x line, this line. Okay, you don't know. Okay, so the thing is, if you come to origin along x-axis, y-axis, so what will be the x coordinate?
0.
X coordinate is 0, right? So basically you are coming right?
Correct.
So you have to find the limit in this case. So what is that? Limit 0 to 0, 0, right? And what I have to write here instead of x comma y?
0 comma y.
0 comma y. Then what is the value of f of 0 comma y?
0 by y square.
It's 0, right?
Yeah, 0.
So then what is the limit? It's 0, right?
Yes.
Yeah. So when you are coming to origin along y-axis, then the limit is 0, right? So here
Yes.
L is 0. The next question is asking what is the limit of the function when you are coming along this line y equal to 3x, right? Okay, so what do you want to compute now? Zero, zero.
F of x 3x.
X, y, but with respect to some condition, this x coordinate cannot be like this x, y coordinate cannot be anything. You have some relation. What is the relation? Y equal to
3x.
3x, right? So this I can write limit x 3x tends to 0 f of x comma 3x. So this one, so this is equivalent to the fact that x tends to 0, right? Both are the same thing. X 3x tends to 0, 0 is same thing as x tends to 0.
Yes.
So I can write that limit x tends to 0 f of x comma 3x. So what is f of x comma 3x here? So this is 9x square
by x square plus 9x
square. So this is nothing but limit x tends to 0 9x square by 10x square, right?
Yeah.
And I can cancel x square, right?
9 by 10.
So then it's basically 9 by 10, which is 9 by 10. As you can see, what you are getting, if you are coming to origin along y-axis, then the value of f of x approaches to 0. But when you are coming to origin along y equal to 3x line, then the value of the function approaches to 9 by 10. So as you can see, when you are coming to origin from two different paths, at least through y-axis and through this line y equal to 3x, you are getting to different limit, right? So that's why the limit doesn't exist. Clear? Why in this case limit doesn't exist?
Yes.
So what is the value of L?
No,
9 by 8, 9 by 10.
Okay,
no,
9 by
for
10.
different case, for the first case it's 0, for the second case it's 9 by 10. Okay.
But limit doesn't exist. In
Limit
case of
doesn't
7.
exist. Okay, because limit certainly it's when you are coming to origin using two different paths, the value of L is different. Okay, but to say that limit exists, you should get the same L. But in this case, you are getting different L. Okay.
So in this case, if the question was like this, what is the limit, and the options were given like 0, 1, 2, not applicable. Here indeed the answer is not applicable, but that goes
Not
via
applicable.
this not valid, not there.
Not
limit doesn't exist.
Yeah.
Defined,
Yeah. Then see, if someone will ask you what is the limit, then your answer should be limit doesn't exist.
Limit doesn't exist. But to arrive at that, since the earlier approach we could not deploy here because the equation doesn't hold the earlier one you suggested. So I have to find out two such straight lines through which I have to find out that this give me different results of L.
Yes,
is it?
Yes. So as I said, like to approach this problem, first you have to make sure whether limit what you want to show. Okay. So so in more or less to answer this question, you have to know the answer. Okay. So if you know the limit exists, then you have to go, then you have to prove it. Okay. So if you know that limit doesn't exist, then you have to try to find different paths for which the limits are different. Okay. So basically I'm doing in a reverse way, you can see. But
you know, just to
anyway,
a priori know that, how will someone know, for example, limit exists or doesn't exist?
It's so the thing is, in most of the cases, like not most of the cases, at least the cases that you are going to see in this course is pretty easy to guess.
Okay.
For example, as you can see here, what is the degree of this polynomial? The above one, 2, right?
2.
The degree of the below is 2. Okay, as I have mentioned it here, like if the degree of the both denominator and numerator are same, and then
highly
almost,
likely.
Mostly then the limit doesn't exist.
Okay. In that case, limit doesn't exist, right?
Yes.
Where degree are same, right?
Yes.
If the numerator is more than the denominator, the possibility to exist.
Yes, if the degree of the numerator is more than the degree of the denominator, yes, then high chances that the limit exists.
Sir?
Yes.
When the limit does not exist, it means the function is not giving a proper information at that point. Is it what, sir? Since you are taking different paths, sir, so for different paths, the function is giving different values.
Yes, true.
So at that point, we are not getting a proper information about the function's behavior or its output.
No, output. See, output is you always know the output of the function. Now, see, output of the function is completely independent from the fact that whether the limit exists or not. Okay.
So if it does not exist, we can say that discontinuous.
Yeah, exactly. The thing is, discontinuity is okay. Like it's the thing is, even it's a slightly you are imposing certain more conditions. Okay. So the thing is, okay, the thing is, the function is not behaving uniformly, okay, from all the different directions.
So that is called not continuous. Or
no. The limit doesn't
exist.
exist. Okay. So the thing is, the function is not behaving uniformly from all the directions.
But it means the same thing, na, sir. If limit doesn't exist, it means the function is discontinuous at that point. That's what he's asking.
No, that is true. Okay, that is true. But the converse is not true. Okay.
So at that point, sir, we cannot.
If you just I'll come to that. Yeah, sorry, like just a minute. I just want to, so limit, if limit doesn't exist, that means discontinuity. That is true, but this converse is not. This part is not true. Discontinuity doesn't imply that limit doesn't exist.
It can exist.
Why, sir?
Sorry?
You mean to say limit can exist for discontinuous function?
Yeah, it can be a discontinuous function, but still the limit exists. Okay.
So that will be a removable discontinuity.
That is a different thing. Okay. So you can remove that. That is a different thing. But you have, for that, you have to change that function. Right?
So this can only happen if the limit exists and the
value of
the function is not the limit.
Yeah, different. Yeah. For example, if I will change from here to 0 to say 1.
Yes.
Okay. So in this case, limit exists, but this function is not continuous.
Okay. Yes, sir.
Limit exists.
Limit exists.
I see.
Sir, just an extension to that.
Okay, just a minute. What actually extra thing you are doing for continuity? What is the extra thing you are doing for continuity? Only one thing, right? The limiting
function value equal.
The limiting value should be equals to the function value, right?
Yes.
So if you will change the function value, if you define something, then you have this thing. Okay, for at that particular point, see, for when you are computing the limit at 0, 0, okay, that limiting value, certainly you are not using anything from, so you are not using the value of the function at 0, 0, right?
Correct.
To compute the limit. Okay, so if you simply change this value, if you define some different value, so you will get something different here, so then you will not get a equality here. So if you change, just if you change the function value, then you have limiting value, but that limiting value is not same as the function value. Okay. That is the thing. You simply, but as someone already said, like this is actually, there is something called removal continuity. Okay, so you actually you can remove it, but anyway you have to modify it. Okay.
Yes, sir. I was saying, sir, just an extension to this question, like we discussed about continuity and limit. So generally, so is it right that if the function is continuous at a point, then only it can be differentiated at that point, right?
Sorry.
If a function is continuous at a particular point, then only we can differentiate the function at that point,
no,
right?
Then we can talk about differentiability.
Then only we can talk about differentiability, right?
Yeah. So if certainly if the function is not continuous, then certainly it cannot be differentiable. Okay. Anything else? Hello.
I think it's clear.
Yeah.
Yes, sir. Clear, sir.
Yes. Okay. Thank you. Okay. So, okay, how you can solve this question now?
We will do cos y.
Hello.
Yes, sir. So limit xy goes to 0. One minute. Yeah, xy goes to 0. Cos y, that is defined, and limit xy goes to 0. Sin x by x is defined. So we can take the product and calculate the limit at xy goes to 0, 0.
Yes.
Please explain it, sir.
Yeah.
Mute all of us.
Yeah, fine. Certainly I'm going to discuss. So the first option says f is not okay, so whoever, please mute yourself. So the first thing is f of is not defined at 0, 0. So what about the option 1, whether it's correct or it's wrong? Hello.
It is defined.
Okay.
It's incorrect.
It's incorrect. Why? Okay,
it is defined because it is.
I'm muting all of you. Whoever wants to say something, please unmute yourself when you can.
Because at 0, 0, it will be cos y.
True. Yes, true. Whatever Mohan said, yeah, it's true. Because by the definition, f of 0, 0, because if x is 0, so in this case, x is 0. So in that case, it's cos 0, which is, sorry, it's cos y, and y is also 0. Y is also 0. So this is 1. Okay.
So first option is wrong, right?
Sorry?
First option A is wrong. A is incorrect.
A is wrong. A is wrong and B is correct.
Yes.
So the next thing is f is continuous at 0, 0.
It is continuous, right?
It's continuous, but why?
So because cos y is bounded.
Limit is 1.
So mod of sin x by x would be less equal to 1. We can go from there.
Sorry, please.
Value at 0, 0 is cos y.
It is 1.
This is This is
Or
1.
we can check for
You just
limit.
you need to show that limit.
Yes.
Is also 1. Then only you can say that this is continuous, right? So my question is how I can show this one.
How to find the limit?
So we can take mod of cos x, cos y sin x by x. So we can we can take the this will be this will be less equal to sin x by x, means
We are taking mod.
mod of sin x by x.
Yes, true.
So
What is the,
so now
I'll come to that. Okay,
first just mods.
I will come to that. Just let him complete his
yes, so now we can then if we can take away the mod, then this will become greater equal to minus sin x by minus x and less equal minus sin x by x and less equal to sin x by x.
This is so now you are saying, okay, now I'm saying this is right.
Yes, we have to take away the mod also.
Okay, so it's not a problem. Okay.
So now if we apply the limit 0, 0,
then you will get -1 here.
Yeah.
Then you will get limit of whatever is this. This is in between -1 and 1.
Yes. So no, this is not giving the right answer.
Yeah.
How sin x by x is? Okay. 0,
0. Limit actually, see, there is nothing. So there is no term containing what. So this is basically limit x tends to 0 sin x by x.
So that is sin x will be 0, right?
No, so you are saying this one. This is 1. I guess you have to apply L'Hopital rule. So if you differentiate the above one, what you will get? Cos x by 1, which is basically 1. So by applying L'Hopital rule, actually you can show that this limit is 1. Okay. But anyway, this is not going to give you the correct proof. Okay. Because from here, whatever he is saying, from here you can only say that the limit is basically in between -1 to 1, but certainly it's not going to give you the fact that this limit is 1. Okay, you just know that limit is in between -1.
So then we have to apply that product formula. Cos y sin x is sin x plus sin x plus y minus sin x minus y by 2.
Yes.
Maybe that can lead to the result.
Yeah, probably you have to apply that product thing. Then only I guess you will get the answer.
Yes.
So can you work this out?
Yeah. I'll do it. Okay. So you have two cases, right? When x is 0 and when x is non-zero, right? So say for this case, I'm taking x to be non-zero. Okay. So if x is non-zero, what will be the value of this function? What will be the value of this function?
Cos y
the first value, that's cos y sin x by x.
Sin x by x.
By x.
Right. So So what I can do now? Now I can whatever, like maybe Arindam or someone in, yeah.
Yes, sir.
Suggest. Yeah. So whatever he suggested, we can. So now this is basically, it's a function of one variable. So we can simply omit this x part because it's sort of pointless to include that x tends to 0 because that function doesn't depend on x. So now what is this limit?
1.
That is
1. 1 into 1. Yeah.
This limit is also 1.
1.
Yes.
So the product is 1.
Right.
Okay. And similarly, you can consider the case when x is 0. Okay. So if you consider the case x is 0,
Then it becomes cos y.
so here x is 0. Then basically what? This is nothing but y tends to 0 cos y, which is also 1. So in both the cases, actually the limit is 1, right?
Right.
So that means the limit is precisely 1, and which is same as the functional value.
So this continuous, no?
This is continuous. Yeah.
Okay.
This is continuous. Okay, probably. Okay, so okay, this is also, you can mostly you can check that this is actually not continuous. Okay, this function is not continuous. The same argument, you have to take y equal to mx. If you take y equal to x, then probably the limit, if you take the limit along this line, then you will get say 1/2. If you take maybe y equal to 2x, what you will get?
1/5.
Yeah, 1/5. So as you can see, for this part, the limit is 1/2. For this part, the limit is 1/5. So basically for one, if you take this line, then the limit is basically 1 plus 1/m square. Okay, for different path, you are getting different limits. So the limit doesn't exist. Okay.
So even by that logic also, sir, since degree is same in numerator and denominator, so limit doesn't exist.
Yeah. So the thing is, so that is certainly most of the cases it will work. Yeah.
And it is not continuous also, right?
And for continuous, you have to find the limit.
Limit doesn't exist. Once limit doesn't exist, then there is no, so you cannot talk about continuity. So it's not continuous.
So it is not continuous.
So see this process is like, see the thing is, once you know limit exists, then only you can talk about continuity. Okay. Right. If limit doesn't, see, if this is not true, then this cannot be true. Okay. If once you have continuity, then you can talk about differentiability. Okay. If this is not continuous, then certainly it cannot be differentiable. Okay. One thing. Okay. But
here that's a basic doubt, sir.
Yes. Yes.
Yeah. So you first to check the limit. So the function limit exists when it approaches a point. So we can straight away deduce that it is continuous at that point. Limit is existing, right?
Yes. No.
From that.
Yeah. To talk about continuity, first you have to make sure that the limit exists.
The precondition is that limit exists. Limit should exist.
Yes.
Now, once from limit you reach to continuity. From continuity to differentiability, like can we say that if it is continuous, automatically we can reduce that it is differentiable at that point, or how?
No, you are saying if f is continuous,
yes.
Can you conclude that f is differentiable or not?
Yes, sir. Yes, sir.
No. That is not. You cannot conclude. Okay, you have to check. You have to check. Okay.
Separately.
Yeah.
And
for
the converse, can we say that if it is differentiable, can we deduce that?
See, for differentiability, you need continuity. Okay. So first you have to check continuity, then you can go to differentiability, or certainly you can check it directly, but yeah, if f is differentiable, then blindly you can say that it's continuous. Okay. But the thing is, okay, so if you take, why I'm saying, if you take this example, say the graph of mod x, this is continuous at 0, but it's not differentiable at 0. This function is continuous at 0, but it's not differentiable at 0. So if the function is continuous, but you cannot directly say that the function is differentiable. Okay, you have to check it. Okay, so what about this one? Any guess?
So not continuous.
Yes, certainly this is not continuous, right? If you take this line y equal to mx, what you will get? 1 by
x cube.
1 by 3m.
3m.
Yeah. So for different lines, your limit is different. Okay. Yes. So that's why it's not. So that's why this is not, even for this function, limit doesn't exist. So once limit doesn't exist, you can say that this is not continuous.
So here we are substituting the value of y equal to mx, right? And then we are cancelling out the terms, right?
Yes. And what about this one?
So 1 by 3.
It is continuous, sir.
This will exist, right?
This is continuous.
Continuous, because this is, see, this is basically like the sum of polynomials. Okay, so each polynomials, they are continuous at 0, and their limit certainly exists. And if you see, the limiting value is basically 0, and which is same as this functional. And basically,
how 1 by 3.
Yeah, I'll come. Basically, it's even simply you can write in this way. You don't need this thing. Okay. So simply you can write, this is my function for all xy.
Correct.
So it's basically, you don't need the last one. Okay. So when this function is basically continuous function, because all the polynomials are continuous and addition of continuous function is continuous. Okay. Yeah. So someone was asking something from this part. This one.
1 by 3.
No, if you put y equal to mx over here, what you will get? X cube
by
3x square into mx, right? So this is nothing but x cube by 3m x cube, which is 1 by 3m, right? So if you take different lines, the limit. So this limit is basically, so it's the limit is coming in terms of m, means the limit is dependent on the slope of the line that you are taking. Okay, that means if you take two different line of different slope, then the limit is different. Okay.
So, sir, this reiterates the point that whatever knowledge we have in one dimensional, so we have a general knowledge, say x square plus quadratic in general is continuous, x power 4 plus x power 6 it's continuous. So the general applies to here, 2-dimensional, 3-dimensional, whatever dimensional.
Oh, yes. So polynomial function, they are basically continuous differentiable functions. Yeah, whatever you have seen in case of one variable, yeah, same is true over here. Okay, but the main problem is so why one variable is easy is only because of one fact that you have only two different limits, left hand limit, right hand limit. But in case of multivariable, you have infinitely many directions. Okay, so that's why
so the problem comes with generally the rational functions then.
It's because no, it's not like the rational function. Yeah, so it's rational function. Yeah, so certainly the problem you will face problem when the function is rational, but even for other function also, if it is not rational, maybe some mixture of rational and something else, some trigonometric function or something else. Yeah, so then also you'll face the problem. Okay.
Yes.
So in general, if it is a polynomial, we can sit, relax. Okay.
Yeah.
It will be continuous.
Yeah, it is polynomial, then it's certainly. But again, like if I'll change this question from here to here, like suppose this is my question. So if I'll change this question, this is my polynomial, this is not 0, this is 1. Then certainly you cannot see, then this is not continuous. Okay.
Yes.
I'm just
saying.
So you have to see like how the function is defined. Okay. So here actually, since here I have defined the value of the function is 0, and basically it matches with the original polynomial. That's why actually it's continuous. Okay. So it's, as I said, it's same thing as writing this.
Yes, sir. That's actually a very good thing. If you change below value 1.
Yeah.
Yes.
So that is so, yeah. So certainly polynomial, if you are taking only the polynomial function, then you can, they are continuous, even their partial derivative exists, they are differentiable. Anyway, we are not going to talk about differentiability, but again, they are also differentiable. Okay, so I guess I have completed all the questions that I have.
When are we going to discuss the gradient function and
that I am going to discuss Tuesday. Okay.
Tuesday.
Yeah. So basically, my plan was to discuss gradient and this directional derivative together, because see, if I compute all the gradient using what the definition, then I have to do a lot of calculation. Okay. So
sir, what will be the syllabus for quiz 2 planned on 13th of March, sir?
Week 1 to 8. Week 1 to 8.
So entire week 1 to 8.
Okay. Okay. So the thing is,
weightage wise, what will be the?
No, weightage wise, I don't know. And also, if I know, then I'm not going to say it. Okay. So, so the thing is, yeah. So the thing is, basically, there will be very few questions. Basically, you need the concept of week 1 to 4 to solve the question from week maybe 5 to 8. Okay, so that's why this week 1 to 8 is there.
Can we assume it is 80% from week 5 to 8?
Sorry,
sir. Can we assume that it will be 80% from week 5 to 8?
Okay, I don't know. You check the mock paper. Once you check the mock,
I think it happens like that only. Going by past run, it happens like that only.
So, so you assume whatever you want.
When is the mock test?
Mock, I don't know. Like maybe Friday or maybe Sunday.
But sir, this is confirmed now that from week 9 onwards there won't be any question in quiz 2, right? No, that will be an end term.
Syllabus is week 1 to 8. No question will come from week 9. Okay, nothing will come from week 9.
That we have to prepare for end term.
Yeah. Yes.
Sir, just a trivial doubt, sir. Since we are so well connected with the subject at this point of time, we talked about limit, we talked about continuity, and then differentiability, right? Though we are not going to study differentiability for multivariable, right? But for one variable, we say that we find out differentiation to find the rate of change at that point, right? Rate of change, na?
Yeah, basically the differentiation is basically gives you the slope of the line, tangent line at that point. Yeah.
So rate of change is basically the change of one point in x. What is the impact on y in a layman words, right?
Yes.
So say for example, if I have function y equal to x to the power 10, right? Y equal to x to the power 10. So if I carry out first degree differentiation, yes, fx equal to x10, x to the power 10. So if I carry out first differentiation, so it will become 10x to the power 9, right? So how to study rate of change for this function? Because my change is varying from one point to another. Like the moment I put x equal to 1, I am getting a different value. The moment I am putting x equal to 2, so the difference is not constant. What I'm saying. So how
because the graph, because if you draw the graph, then certainly the graph, the rate of change, if you let's say forget about x10, it's even
x3 you can take x3 or
simply you take x square. Okay. For here also, for the rate of change is different, right? So
yes.
So if you draw the graph, then certainly it's not a linear graph. Okay.
Right.
So here you have something different. Here the rate of change is different, right?
Okay.
If you just think about this point at 0, here also the rate of change is different. So if you talk about this one, so here the rate of change is different. Okay. For different point, if you see the neighborhood of that point, you see the behavior of the graph is different. Okay. It's for linear function. If you see the linear function, may say this function. Okay. So everywhere it's same, like it's basically it's moving linearly.
Then how to study rate of change of such functions?
Which one?
Then how to study like x square, x cube, x4?
That is what derivative. No, you are getting that. That's why for different point, the derivative is different, right? If you take 1, the derivative at point 1 is okay. See f dash. The derivative of that function is 2. If you take 2, the derivative of that function is 4. Okay, but for different function, at different point, the derivative of this function is different.
So for just for understanding, so are we saying that in order to find out the rate of change, we have to differentiate it only once, right? Only once, not second order derivative or third order derivative.
Yeah. If you want to talk about the rate of change of that function, that f of x, then you have to only differentiate once.
Only once, right?
Yes.
So then why do we go for second order derivative and third order derivative?
That depends on what you are trying to do. Okay, so see, the second order derivative will give you the maxima and minima of a function. Okay, so it's depend on what you are trying to do. So if you want
after that, like third order derivative,
that is okay. Then you are talking about approximation of a function. Okay, so you are going into Taylor series.
Okay.
The thing is, why actually Taylor series? Why you study Taylor? Sometimes the function are really complicated. Okay, so you try to understand using polynomials. Okay, so if you see, like that is probably the basic idea of Taylor series. So you want to approximate some function using some polynomials. Okay, you want to give some polynomials p of x, which is more or less same to p of x. Okay, with some
no problem.
Sorry.
Sir, mute everyone, sir.
Okay. So you want, because polynomial functions are nice functions. Okay, so you want to study using, if you take some n power derivative, then you will get a better approximation of this function. Okay, so it's as I said, it's depend on what you are trying to do. Okay, what you are trying to achieve. Okay, so different in different area, you have different approach. Okay,
but rate of change is only first order.
Yeah, the rate of change of the function, you don't have to go to all these things. Okay, it's
only first order.
Yeah, first order derivative.
No, I was just confused. I thought that we have to differentiate it till the time we are getting a constant.
No. For the rate of change of the function, you just need its first order derivative. Okay.
So no need to go till the end, till the end we get at the constant value.
No. Only first order derivative will give you basically the slope of that line.
Okay, sir. Thank you, sir.
Yeah. Pritam, are you here? You asked some question in the
Yes, sir. Yes, I'm here. So practice assignment 9, question number 1.
Practice assignment question number 9. So like I guess solution is available, right?
Yes, sir. Solution has been uploaded. So I think it would be better if you open the solution PDF as well. Then it would be faster actually.
Okay, just a minute. Yeah. Yeah, Pritam.
So where is
Question
it?
number 1, he said. No?
Yes, sir. Question number 1.
Oh, question number 1. I thought question number 9.
No, sir.
Page number 6.
Page number 6. Okay. Yeah. Yes. Yes, Pritam.
Okay, sir. So I think this solution would work as long as x and y are of the same sign.
Same side.
Same sign.
Same sign, like positive. If both of them are positive, then it will work. If both of them are negative, then it will work. Why is it so? Probably. But again, I guess you can copy the same method when okay, so you are saying if they are of the same sign, but that certainly will imply that if you take also different sign also, still you can use the same argument, right?
How, sir? Because then I'll not get the lower bound as 0.
Just a minute. No, what actually he proved?
So basically sandwich theorem has been used. So in order to
no, just one more thing I just want to say. He actually proved that limit of mod f is 0, right?
Yes, sir.
So if limit of mod f is 0, then limit of f is 0, right?
Okay, sir.
That is the thing, right? Because he basically he proved that 2 times mod x.
So I understand this in one variable case, but does that hold in 2 variables?
Yeah. That is same argument, right, Pritam? Because if limit of mod f is 0, okay, so the certainly limit of f is 0, right?
Is that a property?
No, like you can apply a sandwich theorem, right?
Okay.
Just a minute. Let me stop sharing this one.
I have done EQ 9.1.
Yeah, I'll come to that. Just give me a minute. Let me complete this one. So that okay. So the thing is, this part is really crucial. Okay. 0. Because it's not true if you'll get some non-zero thing. Okay, you cannot apply this.
Sorry, what did you say? This can be applied.
Yeah, so the thing is here the 0 part is crucial. If I say that limit mod is A, then I cannot say that.
I see. Okay. Oh, this is true only if it is 0.
0, yeah. This is not true in general. Okay. Okay, probably I guess you can use sandwich theorem to prove these things, because let's say f of x is certainly less than mod of x, which is greater than minus mod of x. And if you apply this is 0, this is 0. So that's why the middle one is 0. Okay. It's the same thing you can apply for 2 variable function. Okay, because see, the thing is your codomain is certainly R.
Yes, sir.
So codomain is basically R. So you are not taking R square. So in R square, this mod have some different meaning. Okay. So unless you are in R, you can do the same trick. Is it clear, like how actually now you can do it? Like,
yes, sir.
Okay.
So
okay,
I have a few doubts from graded assignment about the question itself. So can you share the graded assignment question?
Okay, just a minute. Stops there. Practice. Week 9. Which one?
So question number 5. So usually when we say x comma y not equal to 0, we mean none of them can be 0.
Yes. When you say x.
So if we follow that reasoning, then this should be x comma y as a vector is not equal to 0, or maybe the x comma y is not the origin, because if that is not the case, then we have cases where it is not defined as well.
Yes, true. Yes.
Yes, sir. So I would suggest if you could correct it.
No. Which one? Question number 5.
Yes, sir.
No, what is the mistake in question number 5?
So here it's given x for x comma y not equal to 0. This is the thing.
No, if x
it's
comma
not given.
see, x comma y is not equal to 0, equivalent to the fact that x comma y is not equal to 0 is equivalent to the fact that x comma y bracket is not equal to 0, right?
So that is what
till now, right? I have.
Sorry.
Till now, I have heard of the interpretation as none of them can be 0.
Yeah, so here this basically tells you that none of them can be 0, right? X comma y not equal to 0.
So none of them can be 0 includes the cases when 0 comma 4 is also not allowed.
Okay, yes, I got your point.
Yes,
okay,
sir.
Okay. Yeah. True.
Yes, sir.
So this basically exclude the cases 0 comma 4. Okay. Yes, true.
0 4 4 0.
Yeah. Basically the x-axis and y-axis.
Yes, sir. So I think this needs to be corrected.
Yes, true. This is a mistake.
Okay, sir.
Yes.
Question number 9.
Just a minute. Let me. Question number 9. Yes.
Okay. So I had a different question, and it was written y equals minus 1x.
Y equal to minus 1x.
Minus 2x in my case.
So So is that equivalent to y equals minus x?
No. No. Y equal to x, right? So what is written in your question?
Y equals minus 1x.
Okay. Okay, just a minute. No, yeah, that is basically same thing as y equal to minus x. Yeah.
Okay.
Yeah. Actually, probably it's the problem with the parameterization. Yeah.
Okay, sir. And I think so. Basically, this is one question I am doubtful about, but I'm not sure whether you would be answering this because it's kind of hints the answer as well. So, question number 6.
In graded.
Yes, sir.
Which number 6? Yes.
So, for the option, for second last option, phi of x can include a term with can be an expression without the variable x, right?
Phi of x
might be an expression without the variable x. Yeah, okay, sir. This was the only doubt. Okay, sir. Thank you, sir. That's all from my.
Yeah.
AQ 9.1, sir.
Yes, I'm coming to that.
6th question.
Let me share my screen. AQ
9.1, 6th question.
Yes, what is the problem here? This is more or less a definition, right?
I'm not able to see this. I'm seeing something else on the screen.
Okay, you want me to again share that screen? Okay, I thought. Okay.
Sixth one.
Yes.
So here they have asked for the vector. How many of these are vector value functions?
So vector valued multivariable function.
Multivariable functions. So I just saw the right hand side and counted the number of dimensions in each.
So okay, so can you tell me so what are these?
Multivariable, okay, vector value.
It's vector value is also.
Okay, x plus 1, x minus 1 should not be taken because that's not the multi-value.
That is multivariable.
Multivariable, but no, it's not multivariable, it's multivariable. But
no,
not a vector. It's a vector, but not multi.
Second, last option is not a multivariable function.
One, two, three. Then answer is 3. Right?
And option 1 is a multivariable function, but it is not a vector valued function.
So I made a mistake. Now I think I realize what mistake I made. The fourth one, I thought it to be a vector actually. No, because this is f of x, right? So
Yeah. I guess option 1, option 4, option 5.
Yeah.
Option 5. They are not.
They are not.
Yeah. Okay. So any other doubt?
Option 5 is also correct, sir. Huh?
Option 1,
4, 5. Sorry, 6 is correct.
6 is correct.
2, 3, and 6.
Yeah.
Okay. Any other?
And the same. I think third one also. Can you go to the third question, sir? The same AQ.
Yeah.
So here, I thought the option B is given as correct. So I didn't understand because x cannot be -1, right?
Yeah, but certainly you can exclude -1 from your domain, right? So it's saying D is a subset of R.
Yes, sir. But
So
it's not explicitly doesn't say now.
No, certainly no. It's the question is it's we have mentioned it explicitly. Okay, so because it's saying suppose f is a map from D to R, it's a function defined on a domain D, which is a subset of R. So this function you can define on a domain which is a subset of R. So then certainly this can be a function. So I think it's clearly mentioned.
So all are functions, right? In this case.
Sorry.
All the four are correct, correct?
Yes. No. First one is not correct actually.
The first one.
First one is not correct. I guess apart from first one, all are correct.
Why it's not correct?
First one.
If you take x less than 10, then it becomes a complex number.
No. That is not the issue. Like if you take f of 1, not f of 1, let's say f of 10. Sorry, you take f of 11. Okay, so what you will get two values. Yeah, that is the problem. This cannot be a function.
That is the reason.
Yes.
Sorry, even if you take x is less than 10.
No, you need a subset. No, you need a subset where the function is defined. Why you will take for all the values x greater than 10. In that case, x minus 10 is real, but the problem is 4 plus or minus is there. So for a single thing, you will get two different things.
Yeah.
So for just for clarity once again, the reason why I was confused with the second option is like here in the question they said that it's a domain. The function is from D to R. So and D is a subset. So I mean like we can't assume where x is minus 1 is excluded, right?
No, D or R. No. Okay, D is a subset of R. Right. Yes, so yes. D can be a proper subset. D can be equals to R. So so what do you mean by a subset of R? It can be anything, right?
Yes.
Yeah. So then D can be anything, right? In particularly, D can be R minus 1, right?
Yes. Okay.
Yeah. So because we are certainly we are not putting any condition on D. So we are just saying that D is a subset of R. That's all.
R excluding minus 1 you can put none.
Yeah. So in particularly you can exclude minus 1 from
D. Yes. Got it.
Yes. Okay. Any other thing?
Once I look at the list where I made nothing else, sir. Thank you very much.
Okay. Then I'll stop the session.
Thank you.
Yeah. Thanks.
Thank you, sir.